first thing I want you to be able to see here is you've got a p-series. You got 1 over radical n, that's 1 over n to the half. P-series says if this exponent is less than 1, it diverges. So this diverges. All right, that diverges. Here, this is a harmonic series. All right, it's a p-series, a special p-series, harmonic series. Every harmonic series, that diverges. You would just have to know that. All right, and then here, 1 over 2n. What I would recommend here is I'd recommend that maybe you use maybe a limit test or something like that. So let's take the limit as n approaches infinity, all right, of 1 over 2n plus 1, and let's divide that by 1 over n. All right, divide that by harmonic series. If you take the limit of this, you get limit as n goes to infinity. If you multiply by the reciprocal, you get n over 2n plus 1. That limit is 1. And this limit test says that if this limit is finite, well, what happens is both this series and this series either both diverge or converge. Because this is a harmonic series, which we said earlier always diverges, this has to diverge. All right, so your problem here, this diverges. The problem requests for you to determine which of these series converge. Let's take a look at this one. All right, so let's use the same test here. All right, so for this one, let's use a different test. Let's use a comparison, a direct comparison test. So let's compare 1 over n squared with 1 over n squared plus 1. I want you to be able to see that this is greater than that. All right, this is greater than that. And this is a p-series which converges, based on the exponent. So if this is greater and it converges, that means that this series also has to converge. All right, so this is the one that converges. You would identify D as your answer. All right, so rather than waste time, I'd rather get through as many problems as we can. I don't know if you can see that, but you've got 1/3 to the 2k power. You have to examine that and see what it resembles. All right, so if you look at this very carefully, what you have, if you look at this very carefully, you have 1/3 squared. All right, that's another way to say 1/3 squared raised to the k power. And that said, 1/3 squared is 1/9 raised to the k power. All right, so if you look very carefully, this is actually a geometric series. K is 1 to infinity. And the way I teach my students is I ask them to make this in the form where it's in the form of a geometric series, which is a to the n times r to the n minus 1. All right, this is the standard form of a geometric series right here. K is equal to 1 to infinity. So what I ask them to do is I ask them to make this look like that. And if you do that, you end up with 1/9 to the k minus 1 power. 1/9 to the k minus 1 power. Now you just can't change that problem. What I'd like you to do is I'd like you to multiply this by something where it would be the same as that. And what you could multiply that by is 1/9. 1/9 times this would give you 1/9 to the k. So let's evaluate this from k is equal to 1 to infinity. All right. So now this is the same thing as that. But I want you to be able to see that this is the standard form of a geometric series that I showed you earlier. So let's pull out that 1/9. We get 1/9. You're summing from k. K is equal to 1. All right, so k is equal to 1 to infinity of 1/9 to the k minus 1 power. All right, so now they want you to determine what that is. All right, so there is a formula that said if you want to sum this up, you could take a sub 0 over 1 minus the common ratio. All right, so a sub 0 for this problem, if you put in 1, this a sub 0 represents the initial term. So if you put in 1 here, you put 1 here, all right, so you put 1 here, you end up with 2 times 1, which is 2. 1/3 raised to the second power is 1/9. So a sub 0 is 1/9 over 1 minus the common ratio, which is also your r here, which is 1/9. You end up with 1/9 over 8/9. And now you just do a little algebra. I'm sorry, I just cut off there. Forgive me. 1/9 times 9/8. That 9's cancel, and you get 1/8. Final answer. So you choose A here. All right, these are AP exam-like problems. All right, so final answer would be A there. All right, so let's look at another one. Which of the series converge? I just want to do problem after problem after problem. Get a little calculus practice here. All right, so which of these series converge? This is a P series where n, your exponent, is greater than 1, so by definition that converges. All right, that converges. All right. Over here, this is an alternating series. That's an alternating series. So with an alternating series, you take the absolute value, and you have to meet 2 conditions. The first condition is the limit 0. All right, if you take the absolute value of this, you end up with 1 over n. Now, is the limit of this 0? Is the limit as n goes to infinity, is that equal to 0? The answer is yes. All right, so the answer is yes. So the limit is 0, and you also have to ask your question, if you continue to increase n more and more and more, is each term decreasing after that? And the answer to that is yes. So if both those conditions are met, you're working with a converging series. So that's converging. All right, so those two are converging. Now let's look at this one. One of the things I've told my students is if you see that n there, that's a indication that you could possibly use that limit, actually the ratio test. The ratio 2 to the n plus 1 over n plus 1 squared. Let's divide that by the original series, 2 to the n over n squared. All right? And what we told you is if this limit ends up being less than 1, you're working with something that converges absolutely. All right, so let's evaluate this. 2 to the n plus 1 is the same thing as 2 times 2 to the n. All right, and that's over, oh, I'm sorry. Well, yeah, this is a limit, so I forgot to put the limit there. All right, sorry about that. So what we have is we have the limit as n approaches infinity of 2 times 2 to the n, and that's over n plus 1 squared. All right, and let's multiply that by the reciprocal, which is n squared over 2 to the n. All right, so now there's cancellation here and here. Let's pull out that 2. All right, let's pull out that 2. So what you end up with is 2 times the limit as n approaches infinity of n squared over n plus 1 squared. All right. So if you evaluate this limit, you would get 1. The limit of this is 1. So you get 2 times 1, which is 2. All right, 2 times 1, which is 2. And this ratio test tells you that if your limit is greater than 1, if it's less than 1, it converges absolutely. If it's greater than 1, which is ours is, that tells you that this diverges. So this diverges here. This diverges. The initial question asked which of the series converge, the first and second one. So for this particular problem, you should use C. By the way, this is a test. This is a test that I gave my students yesterday. My calculus class, I gave them this test yesterday. If you take the limit for this problem, you see n and n here. You take the limit as n approaches infinity of n over 2n plus 3. If you take the limit of that, you can divide each term by 1 if you like, but hopefully you can see that the limit of this is just going to be something finite. The limit of this is going to be half. All right? And if the limit is half, that's a giveaway that this series has to diverge. Because the only way this series is going to diverge, the only way that there's a possibility of a series converging is if the limit is 0. All right, so that you should know. All right, so for here, this diverges. All right, so that one's not too bad. We're going to come back to this. Let's finish up with this while I think about what tests we can use for that. All right, let's look at another one. Let's try to get through as many of these as we can. For this particular problem, you want to analyze whether this converges or diverges. I'd like you to be able to see that you can integrate that. You can integrate that. So the test that I would use here is the integral test. So let's assume that you could integrate this. We have x over radical x squared plus 1. All right, so you can integrate that. If you integrate this from 1 to infinity and you get something finite, that's proof that this series converges. All right, so you can integrate this by using u substitution. U is equal to x squared plus 1. Du is 2x dx. All right, so let's take the antiderivative of this from 1 to infinity. You get, pull out that half. You get 1 over dx there, and you're going to get u to the u to the half. You substitute x squared plus 1 to u, you're going to get u to the half. So you end up with 1 half times the antiderivative of u to the negative half du. All right, let's take the antiderivative of this. You get half. You end up with u raised to the half, and then you'd have to divide that by half. So you end up with, you have to divide by half. Another way to say divide by half is to multiply by 2. All right, so what you end up with here is you end up with just u to the half, or radical u. And let's evaluate that. If we substitute, let's change the limits of integration. This is in terms of u. Let's change the limits of integration. If we put infinity here, we keep infinity. The limit would be infinity. But this is in terms of u. And if we, that's a limit in terms of x. If we put 1 here, we change that limit to 2. All right. So now what you have is you evaluate that. You end up with radical infinity minus radical 2. All right. Radical infinity minus radical 2. You end up with infinity. And what we told you to begin this problem is if you take the antiderivative and you get something finite, that means that this series converges. You did not get anything finite, you got infinity, so that means that this series diverges. Final answer. All right, so I want to go through problem after problem after problem. Looks like we'll have time to do just one more. And I'm sorry, I'd rather do this one than go back up here. What we'll do next week, we'll hopefully have clarity for you on this problem. Sorry, we didn't do it this time. Next week we'll do that. All right, so last one. We have time for one more. For this particular problem, what I would do is I would see you're working with two fractions. You're working with two fractions that can be combined. So you should have learned in your Algebra 2 class, 1 over n squared minus 1 over n cubed. You can combine those fractions. Let's combine them. Common denominator, least common denominator here would be n cubed. So you multiply by 1. So you simplify that, you'd end up with n cubed times 1 over n squared is n minus 1 over n cubed. All right, so now what we're going to do is let's analyze. This is the same thing as that. So let's analyze this series from 1 to infinity. All right, so what we're going to do, we only have a minute left. What we're going to do is we're going to use the limit comparison test here. All right, so let's compare this. let's call this is our A sub n here. Let's make B sub n. Let's make B sub n 1 over n squared. Just analyzing both degrees there. We only have a little time left. So what we have, let's take the limit. Let's take the limit as n goes to infinity of n minus 1 over n cubed divided by 1 over n squared. This is a p-series. That's a p-series that converges. You end up with n squared. Boy, I'm running short on time. Get n squared times n minus 1 over n cubed. All right. So you're going to get n cubed over n cubed. The limit of that, I'm rushing, is 1. Because you got something finite, the limit comparison test says if you get something finite, both these series either converge or diverge. Because this converged, this series converged. Absolutely. So this would be converged. I'm over time. I gotta go. God bless you. Thank you for watching.